Thank you.
Okay.
Right, good afternoon, everybody, and thank you for joining a series of our workshop. Today we have Laurence, Kirk from Extrapy.io. This workshop is around zero knowledge proofs, and he'll guide you through a practical guidance to developing ZKPs for a decentralized app. This is actually useful for a number of the use cases that people are working on. So hopefully you can take a lot of ideas from this workshop, and feel free to ask questions throughout the whole session as and when it's needed. Thank you very much again, Laurence, for coming and teaching in this post-COVID hackathon for us. Over to you.
Great. Thanks, Antonio. Thanks everyone for joining. It's a pleasure to be here again in the last of our workshops, from Extrapy for this. So I hope you find it useful and take away some ideas from this. This is a little different to what we've been talking about so far, in that you can do zero knowledge proofs without any reference to blockchain. But the two do go together very well, and I think it's perhaps down to the popularity of blockchain that has increased people's interest in zero knowledge proofs. So this is the agenda we'll go through today. It's always difficult when talking about zero knowledge proofs to find a nice balance, a nice level to teach at, because you tend to find that there is people either do a very hand-wavy, intuitive idea of what zero knowledge proofs are without going into much detail, or the other end is that people just present a lot of very complex mathematics, which is quite hard to follow, and it probably introduces a lot of new concepts that most people will not have heard of before. So what I'm going to try and do is find some middle ground. So I'm not going to go into as much detail of the mathematics as there is. I'll provide links to further tutorials and papers around mathematics if you're interested in that. But I'll try to go into a little bit more detail than just an intuitive understanding, although that's where we will start. Once we've done that, we'll talk a little bit about what proofs are and what it means to have a zero knowledge proof. We will look then at some of the theory and some of the areas of the research that is currently happening. And I feel that the feeling I get about zero knowledge proofs and the excitement and really the pace of research at the moment is very similar to what I felt perhaps about 5 years ago or so in blockchain. There really was a great buzz, and there really is a great buzz now about zero knowledge proofs. And it's, I mean, I know speaking to researchers, they find it very hard really just to keep up with the number of papers and the amount of progress that is happening at the moment. But then once we've looked at the more theoretical side, we will look at how zero knowledge proofs are being used in the real world. And hopefully that will be useful for you if you're going to be using zero knowledge proofs in your project. And we'll finish off looking at a little tutorial about how to develop a zero knowledge proof using a project called Socrates. So this allows you to build a zero knowledge proof on the Ethereum blockchain. Okay, so let's start with an introduction to zero knowledge proofs. So typically a zero knowledge proof, if we're thinking about one that involves privacy, we have two main actors. There may be a third one, a creator, but often it's just two people that are involved. And similar to with cryptography, where we have Bob and Alice as the usual protagonists, in zero knowledge proofs we usually have Peggy and Victor. So Peggy is what's called the prover, and Victor is the verifier. And what Peggy wants to do is to show that she has knowledge of a secret to Victor, and she wants to present a proof of this to Victor. And she wants this proof to be robust enough that Victor will have to accept it. But in presenting this proof of the secret, she doesn't want to give away the secret. In fact, even more than that, she wants to give away no other information than the fact that she knows this secret. So it really is a binary piece of information. Either she knows a secret or she doesn't. That's the only information that Victor should get from the whole process. Okay. To give of this, one of the examples I really like is if you know the game or the book Where's Wally or Where's Waldo. This is, I suppose, for children, but it involves a cartoon character who's distinctively dressed, but in a vast crowd of other people. And the game is that is to find him within this crowd. Now, if you imagine the situation where Peggy, who is the prover, she has found Wally in this picture and wants to prove the fact that she has found him to Victor. But she knows that Victor likes to cheat, and if she shows Victor where Wally is in the picture, then Victor is liable to say, "Oh yes, he knew that all along, and that's what he thought, and he also had found Wally," when in fact he hadn't. So to create the proof and to show that she knows where Wally is, without allowing Victor to cheat, what she can do is take the book and then take a very large sheet of paper and cut a hole in the piece of paper that is exactly the same shape as Wally is in the underlying picture, and then place the piece of paper on top of the book and do it in such a way that it's not obvious to Victor where the book is underneath the paper, but to place it so the hole is on top of Wally in the picture, so that Victor can see through the hole that Wally is there. So this will prove to Victor that Peggy has indeed found Wally in this picture. But because he can't see where Wally is in the rest of the picture, he can't really see where the book is in relation to the rest of the piece of paper. He doesn't gain any other information about the picture. So that's a very intuitive idea of what a zero knowledge proof is like. So we've proved that we know where, or Peggy has proved that she knows where the Wally is in the picture, but she's given away no other information. One of the more famous examples, and one that illustrates types of proofs, is one involving a pair of coloured billiard balls and a colour-blind verifier. So if you imagine in this that Victor cannot tell the difference between a red and a green ball, that billiard ball that Peggy has. Sorry, there's a typo in the slide there. And so what happens is Peggy wants to prove that these two balls are of different colour, and to prove that she knows which one is red and which one is green. And Victor does not believe her. He does not believe there's any difference between these two balls. And so the way we can go around or create a process to prove this is for Victor to take the balls, one in each hand, and to show them to Peggy, and then to put them behind his back. And then he can choose to either swap them over between his hands or not to swap them. And then he will bring them out again and present them again to Peggy and ask her if he has swapped the balls over. So the theory is, if the balls are indeed different, then Peggy should be able to tell that the balls have been swapped over or not. So Victor can do this, and if he does this once, he can present these balls to Peggy. And if we assume that Peggy can indeed tell the difference between these, then she should be able to correctly say whether he has swapped the balls over or not. But of course, Victor may reason that if he does this once, that Peggy just made a guess and was lucky in that she guessed. It's a 50-50 chance the first time, so maybe she guessed and was lucky and guessed right. So to make the proof stronger, what he can do is repeat the process. So he'll put the balls behind his back again, swap them over or not, then bring them out again and ask Peggy once again to tell if they have been swapped over. And this time, again, Peggy will know whether they've been swapped or not, and will be able to tell this to Victor. And again, the chance of being able to do that on that particular round is a half, but then cumulatively, the chance of the whole getting it right both times is a quarter. So it is less likely that this would have happened from pure chance, but maybe Victor doesn't really believe this and wants to make sure. So he can continue to repeat this process until he gets to a probability where he is comfortable that this could not have been done by pure chance. If Peggy is answering correctly each time, and we're halving the probability each time, then the probability of it being just by chance becomes vanishingly small. And so eventually Victor will be convinced that the fact that Peggy can tell the difference between these balls is because there is some difference and not just because she is making a guess at random. And so this type of proof is called an interactive proof because we go through a number of rounds between the prover and the verifier before the verifier is convinced of the proof. Another example, the 20 boxes example, is about two people who want to see if they're the same age, but without actually telling each other what their ages are. And the way they do this is to have a number of boxes, the petty cash boxes here, but just need a box with a hole in it so you can put in a sticker. So in this case, Bob will buy these, label them with numbers to correspond to the age, and then lock them. But he keeps the key to the one that he has written his age, which corresponds to his age. In this case, we're saying it's 42, and then he gets rid of all the other keys. Then Alice fills in some cards, puts crosses on all of them except one with a tick, and she posts the crosses in the boxes that don't correspond to her age and puts the tick in the box that does correspond to her age. And then she turns away and allows Bob to open the box that corresponds to his age, so the one that he has the key to. He can then look in, and if there is a tick in there, he will know that he is the same age as Alice. If there isn't a tick in there, then he doesn't know Alice's actual age because the tick was in some other box, but he no longer has the key for that. And then also on the other side, Alice will not know which box Bob has opened if she's not observing this. Sorry, there's no question there. So yeah, if you missed the beginning, yes, the recording will be shared. So yeah, don't worry. Okay, so there are other examples involving Sudoku. So those are kind of intuitive examples of what a zero-knowledge proof is like. And but the area that we're particularly interested in is one where we're using cryptography, and we're using some computational method to prove something, to prove knowledge of some secret. And this area really developed around sort of the theory of proofs, the mathematical theory of proofs, and okay, somebody scribbled on my slide, and let me just put that. Okay, this came out of the idea of proofs and proof systems, and there are a couple of concepts that we need to understand about that. One is completeness, and this is the idea that Peggy, our prover, if she has a valid proof, and we have a valid, an honest verifier, then any proof that is correct will convince that verifier with a high degree of probability. And then on the kind of the opposite side, we have the idea of soundness. So even if Peggy is dishonest, and has a considerable amount of computing power. So that's what the computing power is what we mean by the super polynomial time. So even if she has a vast amount of computing resources, she cannot convince Victor that she, of a proof that is incorrect. So as long as Victor is also honest. So there is some probability in here, and there is the idea of people having a vast amount of computing power, and there are limits on this. We are making some assumptions about the amount of computing power available to the participants in our system. But generally speaking, if we're creating a zero knowledge proof, or we're creating a zero knowledge proof system, we expect that these two features hold about the system. So we expect it to be complete and sound. Now, that is very all fine from the concept of the proof itself, but we haven't said anything about zero knowledge. So in addition to those things, we want the idea of some zero knowledgeness, as I call it there. And this is the idea, as I said before, that when presented with the proof and accepting the proof, the verifier will not find out any other information other than the fact that the proof is valid or that it is not valid. And really, if you look, we'll see this later when we look at the practical example, the proof itself on a computer is nothing more than really a piece of data that is put together by the prover, along with a system that allows the verifier to check that proof. Okay, we'll just go very quickly through kind of the history of zero knowledge proofs. It's because it's interesting that they've been around for a fairly long time. They came really about initially in the 80s. There's a really good article there called The Cambrian Explosion that goes through this. So the first paper that mentioned that really brought or invented zero knowledge proofs was in '84, and oddly enough, it wasn't accepted for quite a while. It really made no impact for quite a while, for a number of years. But written by some of the great cryptographers. So Micali, in fact, you may know, was the founder of Algorand in the blockchain space. And over time, and initially also where this came from is interesting as well, because this came out of proof systems. And it was really, people had kind of made some assumptions about the verifier being honest. And this zero knowledge proofs came around from the idea of what if we don't trust the verifier, and how can we create systems that are kind of fair from both sides and don't allow either side in this situation to cheat. So a number of papers started getting published around this area, and it really did take quite a while to develop. Really, initially things were quite difficult and required a lot of computation. It was not very practical, but over time progress was made, and then particularly with Jens Groth in 2016. We got a really practical way of doing zero knowledge proofs. We started to get some protocols, some systems, which I'll cover later on, which made it really practical to start to produce proofs in systems. Now, there are different types of zero knowledge proofs. The ones that Jens Groth started are called SNARKs, and I'll explain in a minute what they are. We've had very similar naming then. We get some of the things, we've got SNARKs, we've got STARKs, we also have bulletproofs. There are a number of kind of systems of generic zero knowledge proofs. But in addition to those, often people create their own zero knowledge proofs out of cryptographic primitives, very much to suit the use case that they have and to suit the project they're working on. And it's quite difficult if you're teaching about zero knowledge proofs or exploring this area to get a good taxonomy around zero knowledge proofs, because they don't easily fit into anything, and much less easy than, say, if you're talking about blockchains, which develops in a much more linear fashion, I think. Zero knowledge proofs, there are various primitives and techniques that people have linked together and have used in different ways to make zero knowledge proofs. But it feels much more ad hoc. And although what I will be talking about, I'll be very much concentrating on SNARKs today, which are very good general purpose means of producing a zero-knowledge proof. They are by no means the only way of doing it, and it's worth thinking when if you need a zero-knowledge proof, there may well be a simpler way to produce the proof rather than using one of these generic proving systems. And you can see that in this. I mean, the initial examples when I spoke about the intuitive idea of a zero-knowledge proof, we spoke about pieces of paper and billiard balls. So zero-knowledge proofs are not necessarily, you don't have to have the sort of complex cryptography for them, although the way they are used and the way they are used on blockchain, that really does lend itself to that. Okay. So let me just find. Okay, there we go. So yeah, as I was saying, so they're not one particular cryptographic technique, and there may be very simple ways to it, but we're going to look in particular at ZK-SNARKs. And now the acronym stands for SNARK stands for succinct, non-interactive argument of knowledge. So interactive, we've come across in that's the idea that we can have interactive or non-interactive proofs. So an interactive proof may be fine where if the users have a shared channel and there's some synchronous process happening. But in the case of, say, the blockchain, it is much more useful to have something that is non-interactive. So it's much better if I can present a proof and just do this as a one-off process, present this proof to a verifier who then would have to accept it. And as we'll see when we do the practical example, we produce this proof and then we can get it verified within a smart contract. The succinct idea is that we want the proof to be of a reasonable size. So, I mean, back when these were invented, I think proofs could be extremely large. Now we get them down to just a few hundred bytes. So they're easy to store, they're easy to transmit, much more practical from that point of view. The last two parts are more from a mathematical point of view and about the rigorousness of the proof, really. So if it's a proof of knowledge, we're saying that not just that some secret exists, but that I know the secret. And if we're talking about an argument rather than a proof, this is really, again, about the amount of computation that is needed to get around this and the assumptions we are making about the computational power of the people involved in this. Now, just to give you a quick idea of the flow in this, this is talking here about the Socrates project that we'll look at later. Excuse me. So typically, if we're creating a zero-knowledge proof, a SNARK in Socrates, we will write and compile an algorithm using a higher level language, a DSL. And then the creator or the prover generates what we call a trusted setup, and I'll go into this in more detail later on. We then export two pieces of information, a verifier key and a prover key. These are, it's perhaps a misnomer to call them keys, as they are not keys in the sense of being like private keys, private key pairs, or anything like that. But they are needed for the rest of the proof. The prover then computes a witness. In the case of Socrates, this is perhaps a trivial step. It's really just recording the secrets that the prover has. The really important step is that the prover generates a proof and uses the proving key for this. And this is the proof that then is given to the verifier, and this will be via some side channel. It will not be done via the blockchain necessarily. This can be passed in any way, but it would be a piece of data that is passed to the verifier, that the verifier can then put into the verification code that he has. So in our case, this will be a smart contract. So just a simple diagram to show that. We start off with the algorithm which defines our proof. We turn this into some mathematical representation, and really all of the theory I'll talk about is very much about this mathematical representation. This gives us a proving key and a verifying key. The proving key is used along with the secret to create a succinct proof, and the verifying key is used to create some code, some algorithm to verify that the proof is correct. More rigorously, we say that we have 3 algorithms in our SNARK, and they're defined as we have them here. Some program C that is really defining what we wanted to prove, whatever it is, whatever our use case is, and then we'll have a proof and a verification system or algorithm. But the one important thing here is that when we're creating this initially, we have this secret parameter called lambda that is used when we're creating our proving and verifying keys. Now, this is something that is needed for ZK-SNARKs, which is not necessarily needed for other types of zero-knowledge proofs. But it is a feature of ZK-SNARKs, as we shall see. And we say this is a secret parameter that is created when we create our keys for our proving system. The other piece of terminology we need here, we call the secret that Peggy has, that our prover has, the witness. This is just a tradition that we call this a witness. And the witness interacts with the program C in the fact that the witness applied to C along with X, and now X here is some public parameters. If the program is correct, has been correctly created, then this witness, along with any public parameters, will, when passed to the program, return true. So this has some aspect of zero knowledge here, in the fact that our program is only going to return true or false. And it is important to note that along with the secret parameter, the witness, we can have public parameters as well. So these are parameters that are known to anyone. We're not trying to keep those secret, but they may well be used in part of our proof, whatever our use case is. Now, the trusted setup is a very interesting thing, and it is this secret parameter lambda. And I think when these papers were initially when the theory was initially brought out, not much notice was taken of this lambda. But when this was done and people tried to implement this, it was realized that this secret parameter lambda was quite important. The reason for that is that if this secret parameter is known and is leaked to someone, they could then use that to produce false proofs. Excuse me. So typically, if we have our program C, this is our algorithm that is we're using for our proof with some public input. If you know lambda, you can produce a proof. So here we call it PR2, such that when this is verified with our verification system, it will always evaluate a true, even though the person who created this proof didn't actually know the secret W here, our secret witness. So obviously, when you're creating your SNARK, it is very important that this parameter lambda is kept secret. And because of the fact that this is such an important thing and it could be so destructive, this has become known as the toxic waste in the setup of the ZK-SNARK. So this part of creating the ZK-SNARK is called the trusted setup, and it is the process we go through to create the keys. And this parameter lambda was called the toxic waste. I think this was coined by the people who created Zcash. The idea is that it is, something that you want to get rid of, and that you don't want it to be publicly available. And to get around this and to make sure that this that the trusted setup is done correctly, people producing these systems have ceremonies to do this trusted setup, so that they can do this in a way that no one person would get this secret parameter lambda. And so the way they do this, they have these ceremonies, and this one, Aztec, are a company that's have a zero knowledge proof system on Ethereum, very interesting system and used for a lot of financial products. But to set up their system, they went through this thing called the ignition ceremony, and this was their trusted setup before they could start using their SNARKs. And to prevent this lambda, this toxic waste, being revealed to anyone, this trusted setup is in the form of a multi-party computation. And what this means is that this is a computation that many people take part in, but no one person will ever get to be able to get the whole of this secret parameter lambda. So this is done by multiple people. It's a computation that overall does this trusted setup and effectively has this secret parameter, but no one person doing part of this computation will be able to learn what this secret parameter is. The setup with Aztec took part almost a year ago now. I took part in it along with a few hundred other people, and it just involved running some computation on your laptop and then returning this to Aztec. It took quite a long time. I mean, the whole thing took a couple of weeks, I think, overall. And it was done by different people in turn. And the idea behind the multi-party computation is that if it would require everybody involved in this computation to collude for this secret parameter to get known to everyone. So as long as one person in the ceremony is honest and does not collude with everyone else, then you can trust the whole ceremony. And so we had a few people doing this. If anybody could join, so if you're worried about the ceremony or worried about the setup, then you could join, and you would know that because you are honest and you're involved in the setup, that the whole thing will work, because you would have to collude for it to be dishonest. And interestingly, the first person in the ceremony was Vitalik Buterin, the inventor of Ethereum, which made me think that maybe they didn't need to carry on with the rest of the ceremony, because I think everybody trusts him anyway. But after him, we had a few hundred other people, and the whole ceremony completed. And I think everybody was satisfied that it happened properly and that this secret parameter is not known to anybody. And so therefore, we can trust the setup for Aztec. And a similar thing was done with Zcash. This happened a couple of times. They've had a couple of versions. The initial one, I think, only had a few people, about half a dozen people involved. The second one involved more like 100 people, I think, and involved some very interesting computation. Some people, I think one person got some radioactivity from Chernobyl and then used that to generate some randomness, which is then used in the computation. So people were very inventive about how they did this computation for Zcash. And so SNARKs generally require the setup, and there are different means of producing SNARKs. So here are some of the possibilities. often based on +16, but these require a setup, and it is seen as a cost. And people have tried to find alternatives to this. I can understand why. I mean, obviously, if you have to spend a fortnight going through this process first of all, then that's annoying, perhaps. But I think there's also advantages to this. I mean, it's a great way of getting a community of people together and getting these people involved in your project. So I think there are advantages and disadvantages to having a setup. But as we'll see in a moment, there are also alternatives that don't require a setup. Partway to that idea of having no setup, we've got some recent advances in some new, some new algorithms such as Sonic and Plonk. Plonk is the one that is used by Aztec. It was invented by them. And the idea behind these is that the setup can be reused. So rather than having to go through the whole process again, if you change some aspect of your system, with these setups, Sonic and Plonk, they have the idea that you can reuse some of the computation. So they're getting towards the idea of a trusted setup not being such a burden for your system. If you look quickly at the areas of research, so people have been trying to improve the way SNARKs work since really the major breakthrough happened in 2016. Got some interesting ideas around recursive SNARKs. As I say, there are also alternative zero-knowledge proof systems other than SNARKs, and people are starting to look particularly at post-quantum cryptography because SNARKs, for example, do rely on some assumptions that depend on that will be affected by quantum cryptography. So people are also trying to find zero-knowledge proof systems that will still be safe once quantum cryptography becomes more practical. I'll just go through this very quickly. Improvements people have made, that this is happening at the moment, and people are making improvements to the cryptography behind SNARKs to make them faster, to make them more efficient. One really interesting idea is this idea of recursive SNARKs, and there's a couple of links there to papers. One of the very interesting project in this area is from O1 Labs, who have the CODA protocol. And the idea behind this is that they want to produce a blockchain which is extremely succinct. So as you'll know, if you're developing on Ethereum, if you want to run a full node, you have to, an archive node, you have to download a great deal of data. The idea behind CODA is that you wouldn't need to have as much data because the way it works is that you progressively produce proofs that the latest additions to the blockchain, so the latest block, is correct along with the other blocks. So you take, so assuming you have a proof of all of the previous blocks in your blockchain, one particular SNARK, which is a succinct proof that blockchain is correct, that all of your Merkle trees are correct, all of your signatures are correct. Then you can take that proof, which is small, it's a succinct proof. You take a proof of that, incorporating the latest updates to your system to produce a new proof that the whole system is correct. And again, you have a very succinct proof that the whole of your blockchain is correct. And so in this way, you get a very small blockchain size. There's more to this. You do still need some archive nodes that can go and get you some state. But really, in terms of the proving of your blockchain, it's no longer the case that you have to go back through all of the headers and verify all of the hashes all match up in your Merkle trees, going back through all the blocks. You can just take your small proof and then verify that, and you'll know that the rest of the blockchain is correct. Another interesting idea is dApp, that where so far I've been talking about a prover and a verifier, really just two actors getting together to do this. With dApp, you get the idea that there's a distribution for the proof. So it's like a distributed computation, and this is done to improve performance. So if we don't like trusted setups, there are alternative means of doing zero knowledge proofs. And one of the major ones are called SNARKs. So this stands for Scalable Transparent Arguments of Knowledge. So a very similar idea to a SNARK, but it has some different underlying assumptions. And the ones for a SNARK are quite different. So for a SNARK, they don't require this trusted setup. In fact, all the people have to do is to have an agreement around some common reference hashing mechanism. And once you've done that, then you can carry on, your prove and verify can carry on and produce your proving system. And this underlying assumption can be quantum resistant. So you can be sure that SNARKs will work even after we have some feasible quantum computing. I won't go into much more details about those. The scalability here is shown is to show you that how they scale much better with the complexity as well. So as you shall see, as you make your SNARK more complex, more computation is required, and this can be a limiting factor. So SNARKs are thought to scale better from that point of view. Another type of zero knowledge proof, another alternative, is bullet proofs. Often they're more about proving that something is in a given interval rather than being a more general proof of knowledge of a witness. And people have built systems around those, so there's some links there to those. Just to compare those in terms of performance, what you'll see is that the SNARKs are quite a nice nice compromise for what you want, in the sense that they're quite small. They're quite small in terms of the proof. They're not quantum resistant. They require strong cryptographic assumptions, so that's bad. But the complexity of the verifier, for example, is constant, whereas with SNARKs and bullet proofs, it is not. And for the prover, they're the same as the bullet proofs, and better than SNARKs. So they make a nice, they're a good sort of general purpose proving system. I won't go into sort of post-quantum cryptography really, just that there's some research going into things like and there is then, we're getting things called SNARKs based on that. So a lot of research going into this area, really about making the underlying cryptography, either more efficient or more quantum resistant. Okay, so let's look at ZK-SNARKs in a little bit more detail. We don't have a lot of time for this, so I can't go into much detail. The notes, I've taken this from the tutorials we give in our workshops. So those tutorials or those workshops, we spend a whole morning going through this. So obviously this isn't going to be much more of an overview than that, but there are some links there if you want to go into more detail. There's also a maths primer, because a lot of the terminology involved with zero knowledge proofs is new to people. I don't think it's necessarily that much more difficult than any other area of maths, but it's an area that people generally won't have come across unless they have done, say, undergraduate maths. So there is if you're interested, there's a maths primer just to introduce to some of the ideas around things like group theory and complexity theory. Now, when we're talking about a ZK-SNARK, the way to think about it, the whole process that we're going through, is one about transformation. So we start with some algorithm that we can express in some high-level language, in some function part of a program, and we then transform that into what are mathematically equivalent representations of what we have in our algorithm. But we transform that so that then we can manipulate them in various ways, and then eventually we can produce a succinct proof with this representation that also has this feature of being zero knowledge. And what I will cover the first few steps of this in more detail. The last few steps get very complex. I'm really going to have to just skip over those. But I hope it will give you some insight into the process and the idea that goes behind a zero knowledge proof, particularly one exactly a SNARK, but what goes into that, where as opposed to, when we had the Where's Wally example, this was just a sheet of paper, so you can see how that works. But when we get to something more complex and we're talking about some general computation, I hope to give you a little insight into how that can be turned into a zero knowledge proof and into something useful that can be computed and that you can use on the blockchain and in your projects. It relies very much on using polynomials and being able to reason about polynomials. So polynomials are equations that of the form of some power of x. So some terms in powers of x, so x cubed plus x squared plus some constants. In the zero knowledge proofs, the powers of x that we go to can be very large indeed. So these polynomials can seem very complex. But it relies on an idea, this lemma I quote here, that if you have some polynomials that are different, and you look at those polynomials at different points, then if you calculate those polynomials at different points, then the answers you get will be different. So if you want to check whether two polynomials are the same or not, then if you look at those polynomials at a number of points, and the results of calculating those polynomials are the same, then there's a high probability that you do have the same polynomials. And if the polynomials are different, then there's a high probability that they will be different at whatever points you choose to calculate them. And this is really the essence of what we're trying to do. We want to get our kind of our proof and what our verifier is looking at in terms of polynomials, and we're really trying to compare these and say, do Peggy and Victor effectively have the same polynomial, the same view of of what it is we're trying to prove, and view of the secret. And the way we can do this is by effectively trying to equate these polynomials, trying to equate them at various points. But what's important in doing this, that really addresses the proving side, but what's important when we're doing this is that neither side should be able to cheat when they're doing this. And so when we're doing this and we're comparing these polynomials and trying to evaluate points on these polynomials, we rely on a feature of cryptography called homomorphic hiding, which kind of obfuscates how we're evaluating these polynomials. So if somebody wanted to cheat, they wouldn't be able to know in advance which points they're going to do some calculation on, and so choose points that maybe would work, just for them, but wouldn't really be true generally, and would allow them to cheat. So yeah, two aspects then. So there's the idea of having these polynomials, showing the proof and the correctness and the soundness of our proving system, and the idea of then hiding how we're calculating these polynomials at various points, so that we're stopping people cheating and we're not giving away any other knowledge. So that's really where our zero knowledge aspects come in. But to start off this process, before we get to our polynomials, we start with some algorithm. And if we're using Socrates, as you'll see later, we've written this in some high-level language, and we need to get that and transform that into a polynomial. To do that, we first of all need to do a thing called flattening the code, which means rewriting the code so that all of any intermediate variables are specified and any loops are unwound. From that, we produce something called a rank 1 constraint system, which is a system that embodies all the information within our algorithm, within our little program, into a more rigorous system, which is less about computation and is very much about constraints. And then we can transform that into what's called a quadratic arithmetic program, which is a set of polynomials, which is then the starting point for how we can start to check these polynomials and to create our proving system and to do the rest of our proof. So starting there, so if we, in terms of flattening the code, if the first part here, we have some function. So here we're saying y equals x cubed, and then the function is going to return x plus y plus 5. So here we have y as an intermediate variable. So effectively we have x plus x cubed plus 5. But that is our function written in some higher level language. And then to flatten that, we write it out so that any intermediate variables are specified. And so we have an output variable, and all intermediate steps are specified. So we have intermediate variables for doing the additions and all of the multiplications. And once we have that, we can then produce our rank 1 constraint system. Now, these are misunderstood, I think, by people generally, in that they should not be seen as any kind of algorithm or as being a computation. They are a constraint system, and they consist of a number of sub-circuits doing multiplications, and those multiplications are done on combinations of what are called field elements, which can be multiplied and added together. And these field elements are what hold our inputs to the system. So when we going back here, when we have our input x, which presumably will be the secret we have, that input will be one of the field elements in our rank 1 constraint system, along with all the intermediate variables as well. You can see them constraint systems as being more like functional languages. In fact, they're side effect free. There's no ordering, and you can compose these things together. You can easily bolt these things together. It's easy easier to understand if you draw them out, and they look much more like a kind of a hardware diagram. But this is an example where we have these subsystems which are doing multiplications and additions. They're often called gates, and they are here to, the proof we're doing here is to show that C1 times C2 times, and then in brackets C1 plus C3 is equal to 7. So Peggy is trying to prove that she knows the C values such that that thing is true. And so you can create a circuit like this. Now, this can be done automatically, or people do these also by hand to optimize them better. But either way, we can create a circuit like this, which takes in our C values, which are the inputs to our system, and arranges them with constraints. And yeah, the important thing to remember to think about our system is that these are a series of constraints. And so when the system is set up, if you have put in the correct C values, if you've put in a legal assignment, as we say here, then the system will work. It will, evaluate to true. Everything will be correct. But that's not the case if you have a circuit where the C values are incorrect. But it's not the case to think that really there's some sort of algorithmic flow through this circuit. It is really something you have to take as a whole and think of you constraining your system by the values that you have put into it. So what we've done is we've transformed our computation, our algorithm, into this constraint system. And from that, we can then move it into a set of polynomials. And the way this is done, and I'm not going to go into the details of this, there's some really good explanations of this. So Coder's Errand, the blog, is a very good blog indeed. I recommend that, not just for zero knowledge, but Alex writes very good articles about blockchain and about stability as well. So I really do recommend people to read that. So if you want to go into more details of how we move from this circuit into polynomials, then you can go through there. But it is really through taking these, all of the assignments that we have, all of these constraints that we have within our system, and turn them into vectors. And if you think about a simple algorithm, even a simple one is going to require quite a few of these gates to build a rank 1 constraint system. If you do anything non-trivial, you're going to require a great many of these gates to build your rank 1 constraint system. So you're going to end up with very many of these constraints. And so these vectors that we have, that we're taking these values from our system, these vectors are going to be very large. And so the polynomials that we get are going to be a very high degree. So the degree of the polynomial is the maximum power of x that our polynomial contains. So that is why I said earlier that we may end up with polynomials that with the power of x is very, very high indeed, thousands or hundreds of thousands. So we could have an extremely large polynomial. And we produce 4 polynomials as the next stage. These are known as the L, R, O, and H. It's from left, right, output, and H is a special polynomial that is needed to the process. Again, without going into the whole thing, I can't really explain what that does. But basically, for our quadratic arithmetic program, we do need these 4 polynomials, and there is a process by which we can move from our rank 1 constraint system and transform that into this set of polynomials, our quadratic arithmetic program. And all of these transformations are mathematically equivalent. It's very, this really is a throwback to complexity theory, where you get the idea of problems being equivalent and being able to transform problems from one state into another. So this is a very similar type of approach. We're transforming our problem from one type to another, but doing it in a way that makes sure that these things we have are mathematically equivalent. We've got, all of the information, all of the constraints in our polynomials that we had in our original little algorithm. Okay, so that gives us a program. Then we go into the points, and again, I'm skipping over a great deal here. This is all about the hiding. I'm sorry, I've changed over from Alice to Bob here, Alice and Bob rather than Peggy and Victor. This is taken from the ZK explanation of how their SNARKs work. So that's also worth having a look at. And this is all around the idea of the hiding. So we have these polynomials, and then Bob is able to choose random points to compute the values of the polynomials at certain points. Now, which you can do, again, I won't go into what he is here, but he can calculate these polynomials at various points and show that the equalities exist between these polynomials. In addition to, and then there's the zero knowledge part, and the part that prevents cheating is that we have this idea that we can add random values to these points. So S here is our point, and we can add small values to this to conceal the points that we are actually performing the computation on. And there is also an underlying thing called the knowledge of coefficient assumption, which is used as a cryptographic assumption, but this allows us to prove the equality of our combination of polynomials as well. And it comes back to this idea that if the polynomials we have are effectively incorrect, so if Alice or Peggy as was, if does not have the correct secret in the polynomial, encoded in the polynomial, then that polynomial will not match with the polynomial that is kind of expected by our verifier here when he's checking it against these number of points. So these polynomials don't match, and so he will, if it doesn't match, you will be able to reject this proof with a high degree of probability that it is an incorrect proof, because we've seen that the polynomials really don't add up at a particular value of S. And yeah, as I say, to prevent cheating, we're allowing these values of S to be chosen at random, so that we cannot sort of handcraft our polynomials to look correct for only a few values. Really, you would have to have this polynomial correct for any value that could be chosen. So that is a extremely high level. Well, it's an explanation lacking in a great deal of detail. I'm sorry that I've had to do it that way. It's difficult to go through it without going into a huge amount of maths and explaining all of the maths behind all of this. But I hope it gives you some idea of the process that is involved in a zero knowledge proof, and how we can use features of cryptography to both ensure the soundness of our proof and ensure that our proof is correct, but also ensure that there is no knowledge being passed between the prover and the verifier, other than the verifier gets to know that the proof is correct or not. So that's the hard maths bit over with. Let's look at some use cases of zero knowledge proofs. One thing I found as well with proofs, when you try to apply them to real world problems, and I think if you're going to use zero knowledge proofs in your projects, then you will come across this problem, is the idea of the trust and the validity of the different links within your system. So, for example, you may be able to create a proof quite easily with using a ZK-SNARK, which allows, say, Peggy inputs her age and then produces a proof that that is within a certain range, and then presents this proof to Victor, who can then know that her age is within a certain range without knowing her age. But in a real world, you would also want to think, well, Peggy might be lying about her age here. So you then have to look at the trust assumptions that you have about who is providing the inputs to the proof. Maybe there will be oracles. Maybe you've gone to an oracle to get data that you're going to input to your proof. In which case, you also need then to be aware of what inputs to your proof are public and which are private, and you have to preserve that and make sure that the private aspects, the secret parts of your proof, are not being leaked. Sorry. So that, I think, is one of the hardest parts of the zero knowledge proof in a real world application, is to create it in such a way that you can have confidence in all aspects of your system, from whatever it is that you are using to create some data and input this secret data into your proof, right up to how do you get this to the verifier and how do you prove it. One of the first use cases for zero knowledge proofs was with cryptocurrencies. So Zcash really led the way. People had spoken about ideas around this before. Zcash really did the practical implementation of this, and it's, they've got a lot of good documentation about how they did it. That's been running for a few years. More recently, we've got Wimble and Monero. I think they're both based on bulletproofs, whereas Zcash is based on SNARKs. Just to give you a very quick idea of how Zcash works, Zcash is very similar to Bitcoin, and it's set up in the fact that it uses UTXO, so the idea of unspent transactions outputs. And what the zero knowledge part really is about being able to prove that a transaction that one person has submitted into the Zcash system is valid. So it's proving that the unspent transactions, which we're using as inputs, add up to the outputs from our transaction. In Zcash, this is known as a shielded transaction, because you can have non-shielded transactions. In fact, most transactions in Zcash are not secret, but I think about 3 to 5% of them are. So if you want to keep it secret, you can. So the proof is there to prove the validity of the transaction, the fact that the person can spend the tokens that they try to spend, and that it is a valid transaction that has been correctly signed. It uses the idea of notes and nullifiers. The idea is, once you're creating a note for the transaction, and this is done in a way that preserves, has a commitment to the information you've put in, but does not give away information. And then the nullifier is there so that this can be later nullified. And yeah, as I say, this is done really by hashers mainly, so to create commitments and prevent people from to make sure the nullifier and the notes are tracked correctly, but without giving away any information about the details in them. As well as the as well as cryptocurrencies. One of the major use cases at the moment is around scalability of blockchains. So something that has become more recently certainly more important with the DeFi being so popular. So we have things like rollup on Ethereum. And the idea behind this is that rather than having to process transactions individually, we can, in fact, you can batch them together and then produce a proof, such as a ZK-SNARK, that these transactions are correct as a whole. And then the participants on the Ethereum blockchain don't need to go through and verify all the transactions separately. They can just use this zero knowledge proof that this has been done correctly. This improves certainly people using this. I've seen an increase in the number of transactions per second because of that. One that has come out very recently, Cairo. So this is from Starkware, so the inventors of ZK-SNARKs. So obviously different to SNARKs, but again they're trying to solve a similar problem. And what they've done, this is I think come out the last month or so, is to produce they really expanded the idea of what the proof can do, rather than just being about scalability. They're producing more general computation. So this is effectively what you might be doing in your smart contract, but being able to offload this into a proof in their Cairo programs. And I mean, they had the remarkable achievement of getting 300,000 transactions into one proof. That wasn't, I think that proof took a while. I think it went over 8 blocks or so, so it wasn't 300,000 transactions per second. I think it's more like maybe 3,000 transactions a second, but still quite a remarkable increase in the processing that was available over the kind of standard Ethereum value, which is sort of 25 to 50 or something like that transactions a second. So I think certainly Cairo is an area that we're very interested in, and I think that's going to produce a lot of very interesting products going forward. But both of those use cases on scalability are more about using zero knowledge proofs with the proving the computation rather than the privacy aspect. So in both of those, it's not the zero knowledge aspect that is most important, more that you have a succinct proof of some other larger, more expensive computation. Other use cases, very interesting one. You can go, if you follow this link, it goes to the Los Alamos site in the US. So they've put together a proof around decommissioning of nuclear weapons and nuclear material. So this is, I took from their slides. So this next one, I'm not really sure what Darth Vader is doing there. But the idea is that they have some AI doing this neural network that is involved in proving that this weapon, whatever it is, has been decommissioned. And this involves confidential information that they don't want to share. But they can create this proof, and this proof is a proof of a number of things. It's a proof of data, but it's also a proof that the neural network has worked correctly and has computed the correct result. And then they put this proof together and then send it off to the verifier. And because it's zero knowledge, then the verifier cannot get any information about the confidential information, but can be sure that this proof, whatever it is they're proving, has been done correctly. Other interesting ones in Edinburgh, Napier University, they have a laboratory which is looking at identity. So I think a lot of use cases here, the idea that you can create identities and then use proofs to represent this identity or prove maybe some aspect of that identity. So perhaps it's proving that you have the right to access a particular area or some particular data, or maybe it's proving that you are of a particular age. But to do this in a way that doesn't give away more information about yourself. So it just proves one thing, but doesn't give away any other of your personal information. So I think there are a lot of interesting use cases there. Another interesting one that's come up recently, or I've become more aware of recently, and I think became more popular just recently, is a game called Dark Forest. I really do recommend having a look at this. It's a way of playing a multiplayer online. It's a role-playing game, so it's a way of playing that, where there are zero-knowledge aspects to this game. The fact is you cannot find out the information, which adds to the game. But doing it, if you read the blog and read about how it's set up, you do learn quite a lot about zero-knowledge proofs. So yeah, I really would recommend having a look at that, having a play with it. Okay, so we'll finish then. I'll just go through very quickly the how to develop using Socrates. There are some links there for more details about how to develop with Socrates. Obviously, they have their own website and tutorials. So please take a look at those. We've done some tutorials. We've done one also how to integrate Socrates and Truffle as well. So please check those out. So it's they've introduced a plugin in Remix, which makes the whole thing a great deal easier. You can use a command line for this, but it is easier to use doing Remix. So I'll just go through that very quickly. Apologies for the noise in the background. So if you start Remix, and there's a link to it there, on the left-hand side, there is a plugin manager, the little plug at the bottom. So you need to go to that and load the Socrates plugin. So once you click the plugin manager, it will bring up a great deal of plugins. Go down to the bottom one for Socrates and activate that. And it brings up this on the left-hand side, which shows you the different steps you need to go through. It's a little confusing in the order they have them. I think it's better to think of them in a different order. So it's also the case that it could be different people doing some of these pieces. So the overall process that you need to go through, and this really ties in with my description of zero-knowledge proofs when I explain SNARKs, is that we start off, we write some code and then compile it. We then run the generate setup, which is our trusted setup. So Socrates uses ZK-SNARKs, so we have to go through the trusted setup, and that means we have to go through, and that produces our toxic waste. In Socrates, they don't do anything to look after this toxic waste. So if you're doing this, make sure that you do something to get rid of that toxic waste. Make sure it does not leak, because there is nothing within Socrates to do that automatically. Once you've done the setup, that will generate the prover and verifier keys. You can then, the verifier can then do or the creator can do the export verifier part, which creates a smart contract, which holds the verifier side of things. So it's what the information that the verifier needs from this setup to know that the process is being done correctly. Generally speaking, the verifier and the prover would probably both be involved when you're doing the trusted setup, or when you're doing the algorithm that you're using to create the proof. The verifier may well want to be involved in that to know that that algorithm is correct and is what they're expecting it to be. And once that's been done, then you do your generate setup and export verifier. That creates smart contract on Ethereum you can then use to do the verification and use to automate the verification. The next step, compute witness, is a little bit misleading. It's really just a step where the prover inputs the secret value that she has, plus any public values, and these are stored internally. Is when I was describing the setup, the process earlier, I didn't really have a separate step for this because this really is just to store the secret value, but it's a separate step in Socrates, so you need to do that. And then finally, excuse me, you need to, excuse me. You need to generate the proof. So we have here an example. Apologies for my throat. So this is our program, our algorithm. And what we are trying to prove with our algorithm is that we know some values that will, when hashed, will produce a certain hash value. So the inputs to this, A, B, C, and D, are our secret values that only the prover knows. And what our program does is to take in those input values and take the hash of them, and then check whether that hash equates to a hard-coded value that we've agreed with a verifier. Now, the language we have has some restrictions, and that is why this has split into two parts here. So the size of our variables here mean that our hash has to be split out into an array of two variables. Excuse me. But in the concept, you can just think of this as one variable. So what we're doing is we're taking some inputs, we're taking the hash of those and proving that the hash of those is what we expect it to be. So that's our input program. So first of all, we compile this. So you just click the compile button. And what that does is take that DSL, that's the code in Socrates, flattens it and creates our arithmetic circuit. So it is our rank 1 constraint system. So we've gone from the code, now we've got our rank 1 constraint system with all of our constraints expressed in a circuit. The next thing we do then is to run the setup. So this produces our keys, our proving and our verifying keys. So the verifier needs the verifying key to set up the verification part. The prover needs the proving key to generate the proof. And at this stage, we have the toxic waste produced. So you have to be aware and be careful that it's not leaked anywhere. So you just click run setup and it should complete. Once we have the verifier key, then the verifier can use that to create a smart contract. And this will be done automatically for you in the Socrates plugin. You click export, and this will create a smart contract. It's quite a complex contract. It has a number of libraries full of cryptography, as you may expect. But once that smart contract is deployed, then that means that anyone could put the proof as a transaction input into that contract, and it will then put back a result of true or false, proving whether the proof is correct. So the actual function within that contract that does that is this one called verify TX, and this takes in the variables A, B, and C. B is their arrays, B is a multi-level array, and returns, as you can see, either true or false. Obviously, there's a lot going on, within these pairing functions here, but that is the function that you call from within the contract to verify your proof. Once you have that, you can the prover can then add in the secret value. So in this case, the secret value is 5 and the other ones are 0. We store that. We then generate the proof. The proof takes a little longer to generate. This part here, the remix compatible parameters that you can copy, takes that proof and puts it in a form that is you can easily add into your smart contract, the verifier smart contract, and it looks like this. So this is your proof, and this proves that the approver knows the value 0005, and you can paste this in to the input of the smart contract, and it will come back with a true. And obviously, if you're looking at this proof, you're looking at these numbers here, you could not deduce that we have we have the value 005 from that. There's no way of going from this back to the input values. So that's how you do it in Remix. It's a great tool, a great plugin, and allows you to generate your contracts. Your zero knowledge proof. As I say, there are those links give you guides as to how to write those. I wish we could still do our workshops. Just to give you a couple of photos here. We used to run these. We try to run these every month. This was I think our last one, where we had a workshop and hackathon. We obviously have much more time then to run through them. We have a little hackathon and some prizes there given out to people, the winning team. But that's it. There's our blog site with more details about zero knowledge proofs and all of the tutorials. Thanks for listening to all of that. I hope that was useful for you. Enjoy your hacking and good luck with all your projects. Yeah, and if you have questions now, I'm happy to answer them.
I'm guessing no questions, Laurence.
I think they're all
quite a lot to take. Quite a lot to take in, I guess.
Yes.
Yeah. So I hope the workshop provided everyone with a high level, process and understanding in zero knowledge proof. A lot to take in in one seating, but hopefully you have a fairly good understanding of some of the features and potential use cases. And if you have any questions, feel free to ask now, or perhaps maybe ask Laurence on Slack.
Yeah. Yeah. So.
Thank you, Brendan.
Yeah.
So we can wrap up now, if you like, Laurence.
Yep.
Any final say?
No, just thank you, everyone, but also thank you to Antonio and everyone indoors, and to all of the partners for inviting us along to do these workshops. We've really enjoyed doing them. I hope they've been useful for everyone, and yeah, I really look forward to seeing the projects that come out of your hackathon. I think it's going to be great. Yeah. Thank you.
Thanks again, Laurence. And we have Laurence again with us tomorrow as part of the panel. We have the AMA session tomorrow, so please do join us. It's quite an important session. If you're working on a particular project, if you have any technical or business related question, then tomorrow's session is the one to attend. So hopefully we'll see many of you there tomorrow. Thank you so much. I'm going to end the session now and see you very soon. Thank you.